Hello, welcome to the course UEC 001. In this module, we discuss about the application of junction diode as a clamper circuit. So let's start the discussion with the definition. Okay, so clamper circuit is an electronic circuit which is used to shift the waveform to a different DC level without changing the shape of the input signal is known as a clamper circuit. So usually in the clamper circuit, capacitor is used as the clamping element. The main components in the clamper circuit are capacitor, diode, and a resistor. And with the schematic, the idea will be clear about the type of clamper circuit. So I'm representing with a block diagram. Suppose this is my input signal. V in, suppose plus V and minus V are their peak to peak values, pi and 2 pi, saying that this is my clamper circuit. Then there are two possibilities. Possibility number one is my signal can be clamped upward from the positive signal. There may be a chance that you can see that my signal is shifted. However, its peak to peak value, I'm writing over here VPP is equals to twice V. And if you can see that, if you can recall about your input signal, my VPP is also twice V. That means there is no change in the appearance of my input signal. But if you can see that over here, my input was signal at zero reference level, whereas over here it is shifted to some level of V dash. Okay, so this level V dash, this is a DC level shifting of my signal. So such type of clamping is known as positive clamping. Means the circuit which is used to shift my input signal to the upward side known as the positive clamper circuit. However, the second option I am trying over here, if my signal is shifted to this side, still I am saying that the VPP is my 2 volt. Okay, so you can check now. Suppose I am referring this signal as V double dash, so you can check the signal is shifted at this particular level, which is my V double dash. This is my second outcome, and signal is shifted below to the reference line. So such type of signal is my negative clamping. Is known as my negative clamping. So two types of clamping is possible, either positive clamping or negative clamping. So we have to study these two types of clampers. Let us see the next essential part about the time constant. Tau equals to RC is the time constant required for clamping circuit. So one has to choose the external components resistance and capacitance smartly. So selection of R and C should be important here. tau must be sufficiently large so that the discharging of capacitor during the non-conducting situation of diode, okay, will not affect the working of circuit. Okay, so we have to select this R and C such that the time constant tau, this must be sufficiently large. So now let us see the working, and suppose I am dealing, this is a circuit diagram where capacitor C is used as a clamping element. Input we will supply over here V in diode D. For the simplicity, I am assuming that my diode is ideal. Resistance R is connected, across which we want to find the output voltage V, and say the square waveform is applied. So in order to solve the problem of clamper circuit, so this is my V in 0, T by 2, T, etc. In order to solve the clamper circuit, there are few important steps, and if you follow these steps, so you will get the answer of all clamper circuits. So let me write the step also. Step number one, identify the half cycle that makes diode forward bias. So this is very interesting. In the very first step, we have to identify the half cycle. So in general, either positive half cycle or negative half cycle. If you can recall, in the case of caliper circuit, whatever be the input signal given, we were starting directly from that. But over here, smartly, we have to choose the half cycle that make diode forward bias, because you can see that the aim over here is the charging of this capacitor. And if you can see that there are two paths for the charging of this capacitor. One is through this diode, and second path is through this resistance. And the time, charging time, should be as minimum as possible. So you can see if diode is forward bias, then its resistance will be less. So it is better to charge this capacitor through the path in which diode will exist. Therefore, I have written over here, you have to smartly choose the half cycle that makes diode forward bias so that my capacitor will be charged quickly. Now, the next step is apply KVL and find voltage across capacitor and output voltage V0. So for this case, now do these two things, apply KVL, find the maximum charge voltage across capacitor, and in the same V0. Now the next step is select the remaining half cycle and find V0. So this is simple. Whatever be the remaining half cycle, now do the same thing, apply KVL and find the value of V0. And last, plot the output waveform. So now plot the output waveform as per the output voltage determined in step number 2 and step number 3. So let's see the example of the same case. I am saying that this is voltage, peak value of signal is V, okay, and diode was ideal. So now you can check my diode will be forward bias in the positive half cycle. Okay, so let's apply all these 4 points in order to solve this problem. So step number one, select positive half cycle. Now if you can see the nature of my input signal, it's a flat signal. For the positive half cycle, that means from 0 to t by 2, I will have the value of signal V. Okay, so my diode will be forward bias in that period and capacitor will be charged with the like polarity. So let's draw the circuit diagram for this case. As I have told you that during this period we will have a flat signal, therefore I have marked a flat voltage of V. Capacitor will charge, I'm assuming that with a voltage Vc, these are the polarity, and diode will be replaced by a closed switch, and we have to measure output voltage across here. This is the value of resistance R. So this is my step one. We have selected the positive half cycle. Now, if you can see that if I am applying KVL to this loop, apply KVL. So it is V minus Vc will be equals to 0, which is clearly indicating that the value of Vc equals to V. That means voltage across maximum voltage across the capacitor Vc will be equals to V volts. Now at the same time, let's determine the value of output voltage V0. And if you can see that as it is a closed switch, behaves like a short circuit, that means V0 will be equals to 0 volt. Because in parallel, voltage is same, so V0 will be 0 in this situation. Okay, now the next point over here is negative half cycle now. And for this half cycle, let me draw the circuit first, and you can check during the negative half cycle, my entire signal will be of minus V. So that makes my diode reverse bias, means diode will be replaced by an open circuit. So I am redrawing the circuit. The capacitor was initially charged to a value of V. Now it's a flat voltage, but it's a negative voltage. This value is R. I have to find what is the output voltage in this condition. In fact, I am marking over here, it is 0 volts because we have determined, and in this case, we will see what will be the output voltage. So it was charged to a value Vc, which is equals to V. This is replaced by open circuit and external voltage is V. Now, again apply the KVL, apply the KVL in order to find the output voltage. So now it is my minus V minus Vc minus V naught equals to 0. So this is making my V naught equals to minus V minus Vc. But in the previous step, we have find that Vc equals to V. Therefore, my output voltage V naught equals to minus V minus V or equals to twice V with negative sign. So my output voltage in this half cycle will be minus twice V. V naught is equal to minus twice V. Now the final step is we need to draw the output waveform. So interestingly, we can check my output waveform over here is for 0 to t by 2, output voltage was 0, but from t by 2 to t, it is minus twice. This is my V out. And if you can check, this value is VPP over here is 0 minus minus twice V, so it is equals to 2V. That means VPP of input and output is same. So this is indicating that my uh, given circuit is a negative clamper. So my given circuit is a negative clamper circuit, and amount of clamping is amount of clamping will depends upon VC. So VC equals to V, therefore the amount of clamping is of V volts. So you can check. Now my reference level is somewhere over here, and you can check the initial figure. So it was the initial figure. Let us discuss one more problem. Another problem. Or now I am reversing the direction of diode and connecting a battery also. So let's see what will be the effect of inclusion of battery, and let me increase the complexity of the problem so that I am assuming that my diode is made up from silicon. Okay, and keeping my input signal same as a square waveform. So this is my square waveform. Input V in. Suppose this is V, or in fact I'm writing VP, a different notation, 0 T by 2 T 3T by 2 and so on. And suppose this is a battery of value Vk, and this is my load resistance R, across which we want to find the output voltage V0. Now let's see, identify the half cycle. Let's see the same algorithm. So if you can check, negative half cycle is required to forward bias this diode. Okay, so negative half cycle is used to start the power. And let me draw the equivalent circuit for that negative half cycle. So my diode will be on, as it is a practical diode, so will be replaced by a value of zero point 0.7, a value of battery Vk, output voltage, even that resistance is also there, so it is minus plus zero point 0.7, saying that the voltage is Vc and will charge with the same polarity, minus plus of Vp, and this is my Vk. And I'm saying that my Vk is less than Vp, but this Vk is greater than zero point 0.7 volt. For the simplicity, we have taken this assumption to see the response. Now, apply KVL to this loop. Now, apply KVL to this loop. So, I'm taking a unidirectional, okay, the clockwise direction, and accordingly, we will change the polarities. So, apply KVL now. What we will receive? Minus Vp plus Vc plus zero point 0.7 minus Vk equals to 0. That means what we can have, the value of Vc will be equals to Vp minus zero point 0.7 plus Vk equals to 0. So that is the value of Vc. At the same time, let me find the value of V0 also. So you can check V0 is difference between these two battery, and as we have already taken that my Vk is greater than zero point 0.7, so it will be Vk minus zero point 0.7, that is my output voltage for the case. Now let's see the next half cycle, that is for my positive half cycle. Let's see the working for positive half cycle. And in this positive half cycle, let me draw the circuit over here. And you can see that my diode will be open circuited now as it is reverse bias. So we will measure output voltage across the load resistance R. I have to find this V naught. It was initially charged to a value of VC. Voltage VP, and this is still there. This is my VK. Now you can apply KVL in order to find the output voltage V. So what you will have from this KVL, VP plus VC minus V naught equals to 0. Okay, that means my V naught will be equals to simply VP plus VC, or I can put the value of VC, so it is VP plus VP minus zero point 0.7 plus VK. That means twice VP plus VK minus zero point 0.7. Okay, so now by applying all these conditions, one can easily draw the output waveform, and idea will be clear with the numerical examples. Okay, so this is for the clamper, and interestingly you can check for this situation. This is my positive clamper. So I'm writing over here, this is my positive clamper subject. This is my positive clamper. uh, Let us try to solve a numerical so that we will get the idea. Determine V naught for the network. As shown below, and also plot the output waveform. The given circuit is like this. One capacitor is given, diode is given, series battery is given, value of resistance is given. It is 100 kilo ohm. We have to find output across here. This value is given as 5 volt. Value of capacitance is given as 1 microfarad, and the nature of input signal is given like this. In fact, it is not a symmetrical waveform. In positive half cycle have lower magnitude in comparison to the negative half cycle. So this is very interesting problem. 0 plus 10 volt minus 20 volt V in. This is my T by 2, T, 3T by 2, T2, etc. So this is my input waveform, and we have to determine the output for that case. So assuming that my there is no issue of my this charging, as the frequency of signal is not given, but for the simplicity one can calculate the value of tau, and this will be equal to R into C. So 100 into 10 raised to power 3 multiplied by 1 into 10 raised to power minus 6. So it is second, that is the value of my tau. If you can see that further, nothing is given to this diode, so I'm assuming that my diode is also ideal. So as far as the solution is concerned, let's see, starting with the negative half cycle, because negative half cycle will make those diode forward bias. So select negative half cycle as diode will be on in this. So let me draw the circuit diagram first. Circuit diagram will be simple. For negative half cycle, you can check the value of input signal is minus 20 volt. So I'm replacing this diode by short circuit as it is forward bias. Battery will still present. Input I'm showing with a battery of negative 20 volt. Load resistance is still present. We will find the output voltage across layer. That is my complete circuit, plus minus 5 volt. Capacitor will charge with the similar polarity, so we see minus plus 20 volt, and this is now R. Okay, so in order to find the maximum voltage across this capacitor, apply KVL to this. So KVL equation provides us the information minus 20 plus VC minus 5 equals to 0. This is indicating that VC equals to 25 volts. That means the maximum voltage at which capacitor will charge is 25 volt, and one can see from the observation that my output voltage V0 equals to 5 plus 0. Voltage drop across this diode is 0 as we have assumed ideal, and a DC battery of 5 volt is connected, so V0 equals to directly 5 volt. So during the negative half cycle, I am having positive output voltage of plus 5 volt. Okay. Now let us do the analysis for positive half cycle. So select now the uh, cycle to positive half cycle, and let me draw the circuit diagram first. Diode will be replaced by an open circuit. Resistance is available. We have to find the output voltage across this resistance. Now our capacitor was charged to a value Vc, but in this positive half cycle, my input is plus 10 volt here. This is 5 volt, and you can see that this is my open switch because diode is reverse bias. Diode is reverse bias in this case. So in order to find the output voltage, now apply KVL to this plus X. So what KVL equation gives us? 10 plus Vc minus V0 equals to 0. So my V0 equals to 10 plus 25, that is equals to 35 volts. And you can check uh, this 25 is from the VC because maximum value across VC was 25 that we have analyzed. Now we can plot the curve easily. This is my time scale, output voltage V0. You can check for initial positive half cycle 0 to T by 2. We are not marking anything because my diode was not charged. However, if I am assuming that my input signal is a periodic signal of infinite range, then one can think about that for a previous half cycle. The capacitor will be charged and maybe possible that some voltage waveform you will have. But if you do the simulation of the same on the multisim, then for 0 to t by 2, you will not receive any signal because we people are in a habit to start the waveform from 0 to infinite level. And from 0 to t by 2, as you can see from the circuit, for a positive half cycle, this diode is reverse bias, so capacitor will not be charged. And in the clamping circuit, capacitor is responsible for the clamping. Okay, so we must find the maximum voltage across the capacitor so that can take a judgment by which voltage, by which DC level my signal will be shifted. Okay, so let's draw the output waveform now. So in the next half cycle, that means from t by 2 to t, we have seen that we have determined the output voltage of 5 volt. So mark the value of 5 volt over here. Say this is a mark of 5 volt. And then for next positive half cycle, that means from t to 3t by 2. And for next positive half cycle, we have just determined the value of it is 35. So suppose I am saying that this is the mark of my 35. So it will be value of 35, and then continuously for next like 2t it will be 5, and for next half cycle it will be 10. Okay, so this is the output signal, and this is the mark of 35 volt. So interestingly, now you can check the peak to peak voltage of my output signal, that is my VPP, and you can see that VPP is, it is uh, 35 minus 5, that is 30 volts. And you can check what is the VPP of my input signal. So you can refer over here. VPP of input signal is 10 minus 20, that is equals to 30 volts. So interesting point over here is you can check the shape of signal will not change. It is still 30 volt. So interesting part over here is the level is shifted to the upward side. That means the clamper circuit is a positive clamper. So it is a positive clamper circuit. So my given circuit is a positive clamper circuit. And how much amount of clamping we have performed? So it depends upon the VC, 25 volts. So there is a clamping of 25 volts. So you can check entire negative signal of 20 volt and then to this plus 5 volt. So 25 volt signal is shifted. So there is an introduction of DC level of 25. Okay. So we are stopping here.